EDX Mechanics 1, Mechanics Basic Principles, Newton's Laws. Newton's first law. This states that a body will move with constant velocity in a line or remain at rest if there is no net resultant force acting upon it. This first law explains the natural motion of a body in a straight line at constant speed, and if that speed is zero, then the object would be at rest. This can be summarized as sigma f equals 0 for an object which is in equilibrium. The total force in any direction must be 0. Newton's second law. This states that if there is a resultant force acting on a body, then it will be proportional to its acceleration and it will be in the same direction as it. The second law defines this acceleration as follows and may be called the equation of motion. So basically, if the resultant force is non-zero, it will produce an acceleration, and we can say that sigma f equals ma. The net force, if there is one, will equal ma, mass times acceleration. Notice that if we do have equilibrium, then the acceleration would be 0, and we are back to sigma f equals 0. We're back to the equilibrium condition. Newton's third law. Every action of a force on a body produces an equal and opposite force on a different body. This third law explains equal and opposite pulling forces at the ends of a string which is connecting two particles. So if we have one particle connected to the other and they are joined by a piece of string, we can say that there's a tension T at this end, and according to Newton's third law, there's an equal and opposite tension T at the other end. Example 1a. Here we've got a ladder of mass m leaning against a smooth wall and resting on a rough floor. We're going to draw a force diagram and look at the equilibrium of this ladder. If we remember our waterfall anachronism, we can go through the forces. So weight W, so the weight is straight down and is mass times gravity, so there's the weight. There's no air resistance, there's no tensions, there's no engines, but there will be a reaction contact force. So where the ladder is resting on the floor, there'll be a perpendicular contact force, which I'm going to call R. And where the ladder is leaning against a wall, there is a perpendicular contact force. I can't use R again, so I'm going to call it capital X. F for friction. The ladder is resting on a rough floor, so the ladder will try and slide to the left, and friction will oppose any tendency to move, so F must be acting to the right. If the ladder is in equilibrium, we can now apply Newton's first law. So I'm going to apply Newton's first law. I'm going to take to the right as positive on the ladder. So forces to the right are positive, any forces to the left will be negative. So there's F pulling to the right, so that's a positive F. However, X is pulling to the left, or acting to the left. Since force is a vector quantity and it has direction as well as magnitude, X must be a negative X. It's acting in the negative direction. There are no other horizontal forces, so that total force must add up to 0 because of the equilibrium. So the frictional force is exactly the same as the contact force X. If we now apply Newton's first law, I'm going to take upwards as positive. The only upward force is R, so that's a positive R, it's acting in the positive direction. mg is acting straight down. So again, vector quantities, if it's mg acting down, it must be a negative mg. And that total vertical force must add up to 0 because of the equilibrium. So we have that the reaction force R is exactly the same as the weight mg, as we can see there. Now we're going to look at a slightly different scenario. What about the same ladder trying to rest against a rough wall and a smooth floor? So this time we've got the weight, which is mass times gravity, acting straight down. There is a contact force with the floor, normal contact force, so that's at 90 degrees, R. There's a 90-degree contact force with the wall, X. but this time it's the wall that is rough. So the ladder is going to try and slide down the wall, so friction will oppose that tendency to move, so friction is acting up. So there's my force diagram. If we assume equilibrium, I should be able to apply Newton's first law, and I'm going to apply it horizontally to the right. The only horizontal force is X, and it's acting to the left, so that's a negative X. That total force must be 0 if we have equilibrium, which means that X must be 0, which is impossible. So this example demonstrates nicely that it is impossible to take a ladder and rest it against a rough wall and a smooth floor. The ladder must, in this case, move and accelerate. We cannot have equilibrium. As we can see there. Here we have a car of mass 900 kilograms, driving force 3,200 newtons. There's an air resistance of 1,400 newtons. Find the acceleration. So because the car's travelling horizontally, the road's horizontal, we only really need to look at the horizontal forces acting on this car. So there's two horizontal forces. There's the driving force, which is 3,200 newtons. And although the driving force is actually produced by the wheel moving against the road surface, the best place to put it on to keep things as simple as possible is just imagine a pulling force from the engine. There's an air resistance, which I'm going to put there. Air resistance opposes motion, so that must be pointing backwards, 1,400 newtons. Notice the forces are attached to the car. The only other thing I need to add to this diagram is the acceleration. So this is a double-headed arrow, not touching the car, because it's not a force, labelled A. The car is accelerating, so I'm going to apply Newton's second law. I'm going to take the right as positive, and I'm going to apply it to the car. So forces to the right are positive, forces to the left are negative. So there's a force here pulling to the right, 3,200 newtons, so that's positive. Here the air resistance is acting to the left, so that 1,400 newtons of air resistance is a negative force in this case. There's no other horizontal force, so that net force equals mass times acceleration. The mass is 900 kilograms, and the acceleration, according to my diagram, taking the right as positive, is A. So 1,800 equals 900A, and the acceleration is 2 meters per second squared. Notice the acceleration is constant because the forces are constant. And we can see the method set out there. In this example, we have a girl of mass 48 kilograms standing in a lift, and the lift is accelerating upwards at 2 meters per second squared. We've got to draw a force diagram and find the reaction force from the lift acting on the girls. So there's only two forces on the girl. The only two forces we need to consider, there's the weight of the girl acting straight down. So that's mass times gravity, so that's 48 times g newtons. And the only other force is the lift pushing up on her feet, which is a contact reaction force labelled R. Here the lift is accelerating upwards, so next to the lift I'm going to put a double-headed arrow pointing upwards, labelled 2 meters per second squared. Since the lift is accelerating upwards, I'm going to take upwards as positive. So Newton's second law, I'm going to take upwards as positive, and I'm going to apply the method to the girl. So upward forces are positive, downward forces are negative. R is an upward force, so that's positive R. The 48G, I can see on the diagram, is pointing downwards, so that's a negative force. The total net force acting on the girl equals mass times acceleration. The mass is 48 kilograms, and I can see here the upward acceleration is 2. So the reaction force acting on the girl's feet is 570 newtons. And that's to two significant figures. So here, when the lift is accelerating upwards, the reaction force is larger, bigger than the girl's weight, and that gives you the sensation of feeling heavier. When a lift accelerates up, The reaction force is bigger than your weight, and that's a sensation you get of feeling heavier than you really are. In this question, the lift is now moving at a steady 15 meters per second, and the question says we should be able to write down the reaction force. So this time I'm going to put a single-headed arrow to show the speed, 15 meters per second. So the thought process is we've got constant speed. You wouldn't necessarily write all this down in the exam, but if we've got constant speed, that implies the acceleration is 0, which implies the forces must be in equilibrium. If the forces are in equilibrium, that means the upward force R must be exactly the same as the downward force 48G. In other words, when the lift is moving at a steady speed, the reaction force is the same as the girl's weight, and she has no sensation of acceleration because there is a constant speed. Now the same lift is going to decelerate at 3 meters per second squared, and we're going to calculate the reaction force. I think the clearest way to show deceleration, the lift is still travelling upwards, remember, is to put an upward arrow, double-headed arrow, but label it minus 3 meters per second squared. I think that's the clearest way of showing a deceleration. Put it on as a negative acceleration. I'm now going to apply Newton's second law again. I'm going to take upwards as positive for simplicity, and I'm going to apply it to the girl. So the upward force, positive upward forces are 48G is acting downwards, so that's a negative 48. That net force is going to create an acceleration, and that net force equals mass, which is 48 kilograms, times acceleration, and the upward acceleration is minus 3. So this time we get a reaction force which is 330 newtons. It's interesting here that the reaction force is now smaller than the girl's weight, and that gives the girl the sensation of feeling lighter on her feet when the lift is decelerating. It's only because the reaction force on her feet is less than her weight, so it gives the sensation of feeling lighter, although her weight is exactly the same. It's the reaction force that is smaller. In the next session, we're going to be looking at the Suvat equations.